In this lesson, we're going to look at multiplying radical expressions. And one of the properties that you learned in a previous lesson is this. So remember, you learned about the product rule for radicals. And so the product rule for radicals stated something like this. If you have I'm going to go ahead and use the index c. So you have the c root of a times the c root of b. As long as the indices are the same, then you can rewrite this product as one radical. So that's going to be the c root of a times b. Okay? Now, one of the other things I want to remind you is this, and I want you to think about this as we go through this because some of this is going to be important in our discussion. But and let me go ahead and just write the word simplify. So if I say simplify the square root of x to the fourth power, now we're going to assume that all variables represent positive real numbers, so I don't have to worry about absolute values here. But remember, and you had this in the previous lessons and worksheets, but the square root of x to the fourth is x squared because x squared times x squared is x to the fourth. And one of the things that we saw was that we can divide the exponent by the index, and 4 divided by 2 is a nice number 2. Okay. Now, one of the other things I want to remind you is this, and that's if I had, and I'm going to go ahead and use this. So if I said I wanted to simplify the cube root of 5 cubed, let's say, the cube root of 5 cubed. Now, so what some of you may do is you may go ahead and multiply 5 by itself 3 times. So you may say, well, I'm going to say that's the cube root of 125. Okay, no big deal. You can do that. That is definitely a true statement, right? But what I want you to notice is that the cube root of 125, and although 125 is a perfect cubed, which is 5, 3 is divisible by 3. And so that is just 5, right? 5 to the first power, which is what this is. Okay? Number 3 I want to remind you about is this. If I have the cube root of 5 times the cube root of 5 times the cube root of 5. All right. So according to this, I can write this as the cube root of 5 cubed. Y'all agree? And remember, we just saw that the cube root of 5 cubed is just 5. So I want you to notice is this. Do you see that the radicands are all the same and they're all 5s? And I'm multiplying the cube root of 5 by itself 3 times. So the index is 3. I have 3 cube root of 5. So the answer would just be the radicand, right? Okay. So if I have 4, the square root of 5 times the square root of 5, please tell me what that is real quick. So please don't say the square root of 25. I want you to say what? I want you to say 5. Because the index is 2, so the square root of 5 times itself is just a radicand. The cube root of 5 times itself 3 times is just a radicand. Okay? Number 5, if I have the square root of 2x times the square root of 2x, what does that equal to? All right, real quick, the square root of 2x times itself is just the radicand 2x. If I have 6, the square root of 3, the cube root. Let's do cube root. Cube root of 3y times the cube root of 3y times the cube root of 3y. We know that's just 3y, right? It's just a radicand. If I want to go ahead and multiply that out using the product rule here, then I could say, well, that's going to be the cube root of 3y cubed. But 3 divided by 3 is 1, so that's just 3y. And you learned some of this in previous lessons. And the reason I'm bringing this up is because we're going to use some of these ideas as we go through this topic here, which is multiplying radical expressions. Okay, so let's look at number 1. So the directions will say multiply and simplify, if possible. So it'll say something like this. So it'll say, number 1, the directions will say multiply and then it'll say simplify if possible, something like that. All right, and then we're going to assume that all variables represent positive real numbers. So that way we don't have to worry about absolute values. All right, so represent positive real numbers. Okay, all right, so let's go to number 1. So number 1, let's suppose we had 6 times the square root of 5 times the square root of 15. Okay, now what I want you to think about is this. Now there are several approaches students will take. So students will go ahead and use that property we just saw right away. They'll use this property right here. If the indices are the same, then I can write as one radical. So they'll say this. They'll say, well, I have the square root of 5 times the square root of 15, so I'm going to multiply 5 and 15 together. Okay, you can do that. That is true. So 5 times 15, I'm just using my calculator. 5 times 15 is 75. So then you get 6 square root of 75. Okay? And then you got to now ask yourself, all right, is there a perfect square that goes into 75? And the answer is yes, and that's easy to see that it's 25. So I get 6 times the square root of 25 times the square root of 3. Okay? And now the square root of 25 is 5, so I get 6 times 5 square root of 3, and so the answer is 6 times 5 is 30 square root of 3. Okay? What I want you to notice, though, is this. And so I'm going to try to bring back this idea that we just talked about right here, this idea. So I want you to notice this and think carefully for a moment. You see this 15, you see I have a square root of 5, right? And there's no way I can simplify the square root of 5 because 5 is a prime number. And the only perfect square that goes into 5 is 1. Same thing here. Now 15 is not a prime number, but the only perfect square that goes into 15 is 1. So I cannot simplify these. So what I want you to notice, though, if I wrote 15 as this, so watch, 6 square root of 5, square root of 3, square root of 5. So you agree that square root of 15 is this right here, right? And then notice, what is the square root of 5 times the square root of 5? See, the 5s are listed twice. Square root 5, square root of 5 is what? 5. So this becomes 6 times 5, square root of 3, and then 6 times 5 is 30, square root of 3. So there will be times in some of these problems where it may be easier to use this approach here rather than multiplying the radicands together and trying simplifying the result. Okay? So just keep that in mind. It may be easier to do it this way, or it may be easier to do this way. It depends on the problem. Okay? Number 2, let's suppose we had this. We had, let's see, we have the cube root of 175 times the cube root of 25. Okay? So the cube root of 175 times the cube root of 25. Now, what some of you are going to do probably is you're going to do just like you did this. You're going to say, all right, I'm going to, since these are both cube roots, I'm going to go ahead and multiply the radicands together. Okay, so you can, but it's going to be a big number, right? 175 times 25 equals 4,375. Okay? And so now you got to deal with that. All right, so I got to think about, well, what perfect cube will go into 4,375? And so you got to think of these perfect cubes. So you got to remember your perfect cubes now. So your perfect cubes, I'm going to go ahead and put that on here. So your perfect cubes, and there are an infinite number of those. And so your first perfect cube is 1. 1 cube is 1. 2 cube is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed, 6 times 6 times 6 is going to be 216, and so on, right? So it's going to get, the numbers are getting much larger as we go. All right, so, but those are some of our perfect cubes. There's an infinite number of those. All right, I'm looking at this. You see there's a 5 in the end. Let's see this 125, if this 125, which is a perfect cube, will divide evenly into this. So let's try. So we're going to say 4,375 divided by 125 equals Yep, and it does. And the only perfect cube that goes into 35 is 1. So that's the largest. All right, so I'm going to rewrite this as the cube root of 125 times the cube root of 35. Okay? And so the cube root of 125 we just found to be 5. And then we get 5 times the cube root of 35. Okay? Now what I want to do though is this. I want to ask you this though. Okay, so let's kind of use this approach here with this one. So let's think about the cube root of 175. You see I have 175 and then over here I have 25. I'm just curious, if I divide this by if I divide 175 by 25, what I end up with. So let's see, 125 divided by 25 equals 5. Okay, so I've got some 5s involved in here. And so if I want to, I can think of this cube root of 25 as 5 times 5, right? And then let's think of this as this right here. I'm gonna go. Well, let me go ahead and rewrite this over so that way I can write underneath times the cube root of 25. So the cube root of 175 I'm gonna write as the cube root of this is divisible by 5. So I'm saying 175 divided by 5 equals 35. So that's 35 times 5, right? So this is this. And this right here I can write as the cube root of 5 times the cube root of 5. All agree? Cube root of 25 is 5 times 5. And remember we said the cube root of 5 times the cube root of 5 times the cube root of 5, that's just what? That's just 5. And so I get 5 times this, which is the answer that we got here. Just put the 5 in front and the radical in the back. So the answer will be 5 times the cube root of 35. Okay, so think about the different ways in which you can do this. All right, so we're still using the idea of that product rule. We're just, instead of multiplying the radicands together to get one radical, we're splitting it apart to get multiple products. All right, and notice I used 3 factors here because the index was 3. I used 2 factors here, square root of 5, because the index was 2. All right. Okay, number 3. So let's do number 3. Number 3, let's suppose we had this for number 3. Now, all right, so we have this. All right, we have negative 8. I'm sorry, let's do this. 8 square root of 35 times a negative 3 square root of 5. All right. Now again, what many of you are going to do is you're going to use that product rule and write this as 1 square root. And nothing wrong with that. Nothing wrong with that. So 8 times negative 3 is negative 24. And then you're going to say 35 times 5. Use your calculator. 35 times 5 gives us 175. Okay? And then you're going to think about, well, I've got to figure out, well, is there a perfect square? Oh, remember, this is square root. Is there a perfect square that goes to 175? And the answer is yes. So 25, right? 25. So 175 divided by 25, it gives us 7. And 25 is the largest because the only perfect square that goes into 7 is 1. So I get negative 24 times the square root of 25 times the square root of 7, right? And so I get negative 24 times 5, square root of 25 is 5, times square root of 7. And then negative 24 times 5, so let's see, negative 24 times 5 gives us negative 120 square root of 7. All right? And so that's what you would do. Now, I want you to think about that other way. And I'm not going to do it both ways each time because of the time that we have. But I want you to think about, well, first of all, 8 times negative 3 is negative 24. And I'm going to rewrite this as square root of 35 times square root of 5. Now remember, this is square root, right? So here I have a square root of 5, which I can't simplify any further. 5 is prime. But 35 is not prime, but 5 is a factor of 35. So what you want to notice is this. I want you to think about, well, that's negative 24 times the square root of 7 times the square root of 5. That's what this is, right? And don't forget that this square root of 5. And then notice I have 2 factors of square root of 5, so when I multiply them together, it's just a radicand. So I get negative 24 times this 5 right here, and then times square root of 7. That's this right here. All right, and so I get negative 120 square root of 7. So again, see, you get the same answer. Just think strategically, what is easier for you to think through as you go through the process. And you may try one way and you may get stuck, and you may try the other way and you may be able to get it. Okay? 4, let's get 4. Suppose we had number 4, we had negative 8 square root of 3x times 6 square root of 2x. All right? Now, so I have negative 8 times 6, which we know is negative 48. All right, so that we know. But I want you to look at the square root of 3 and the square root of 2. Now, if I multiply 3 and 2 together, that's square root of 6. And I know that I cannot simplify the square root of 6, right? And then we have the variables. Now, with the variables, I would just go ahead and write that as one radical. So I'm going to go ahead and just use the product rule right away for this. Because the square root of 3, I can't do it like I did here, because the only perfect square that goes into 3 is 1, and the same thing here. And 3 and 2, those are prime numbers, so there's not anything I can do with those. So I get negative 48, 8 negative 8 times 6, negative 48, times the square root of 3 times 2 is 6, x times x is x squared. Now here's what I want you to think about. Remember that square root of x squared. I can simplify this. So y'all agree that this becomes negative 48 square root of 6 square root of x squared. And the square root of x squared is just x. So the answer is negative 48. See, this is just x. Negative 48x square root of 6. Or negative 48 square root of 6 times x. Just make sure if you put the x behind a radical that it doesn't look like it's underneath. Some of you did that on one of your worksheets, and you didn't get full points because you got to make sure that there's no ambiguity there. All right, number 5. Number 5, let's suppose we had 8x square root of 5x times 7 square root of 10xy. Okay? Now, you'll notice that sometimes they'll use parentheses, sometimes they won't. Now, I'll say this, see how everything here is a product? When that second product right here is negative, they will definitely use parentheses, because if you don't, it kind of looks like a subtraction problem. So they'll use parentheses to imply that these two are being multiplied together. Here, the parentheses were necessary because the negative part was on the front end. See this part right here, rather than the back end. So that's why parentheses wasn't here. Here, parentheses are not even needed, but in some examples, they'll use parentheses. Okay, so what I would do here is this. And I'm going to do it both ways, just to kind of show you. So I have 8x, think of this as one product together. So 8x times 7 is 56x, right? So 56x. And then let's think about the square root of 5x times the square root of 10xy. Okay? Now, I'm going to go ahead and multiply this as 1 now. So it'll be 5 times 10 is 50. So I get 56x times the square root of 50. X times x is x squared, and then times y. So that's what I have. Now, you have to simplify the square root of 50 x squared y, and you've done that before. You've done that in previous worksheets. And so when I simplify the square root of 50xy, when I simplify that, the square root of 50x squared y, I get the square root of 50 times the square root of x squared times the square root of y. And the square root of 50, a perfect square that goes into 50 is 25, so I get the square root of 25 times the square root of 2, right? 25 times 2 is 50. The square root of x squared is x. I cannot simplify the square root of y because the exponent of 1 is less than the index. And now this right here becomes 5, so I get 5x, and I'm going to put these two back together. The square root of 2 times the square root of y. I'm multiplying two radicals with the same index, so I can multiply them, write them as one radical. So it'll be the square root of 2y. Okay, so that is this. I'm going to put that here. So I get 56x times 5x, that's a 5, 5x times the square root of 2y. Now simplifying this, 56 times 5, figure out what that is. 56 times 5 will give me, 56 times 5 will give me 280. X times x is x squared, and then square root of 2y. And there's your answer. Okay? Now, I want to show you something. So we all know that 8x times 7 is 48, 56x, right? So we get 56x, and then we have that square root of 5 times the square root of 10. I want you to think about that for a moment. The square root of 5, and I'm going to go ahead and just kind of put that here for a moment. So the square root of 5 times the square root of 10 is what I want you to think about. Square root of 5 times the square root of 10. We know that 10 I can write as 5 times 2. See, there's a 5 there, right? So I can write this as square root of 5 times the square root of 5 times the square root of 2. This is just 5, so that's 5 square root of 2. And so this 5 square root of 2 is what you see here, 5 square root of 2. Okay? So if you need to, and the point being that if you need to kind of just look at the numbers that are underneath the radical like we just did, then go ahead and do that. Most students don't. Most students don't do it this way. For that one, they'll tend to do it this way because the numbers are not that large. And there's some variables involved, so it gets a little bit confusing for some students. And so what I would do here, then, if you wanted to do this other approach like we did previously, is I would go ahead and write this as the square root of 5 times the square root of 10, and then times the square root of x times the square root of xy. Just so what I did was I just separated these two, the square root of 5 times the square root of x, that's this right here, see right here, and then the square root of 10xy, I took out the square root of 10 and I left this square root of xy together. And now I can notice that, hey, the square root of 10 right here, the square root of 10, I can write as square root of 5 times the square root of 2. And then this right here, the square root of x times the square root of x times the square root of y. See, this right here is this. So this is 5, because the square root of 5 and square root of 5 is 5. And this is x, right? Because I have two factors that are square root of x's. So the square root of x and square root of x is just x. And then I get 56x times this 5 times this x. And then I'm going to put these two as one radical. The square root of 2 times the square root of y is the square root of 2y. And so I get 56 times 5, just like we did here, is 280. X times x is x squared, square root of 2y. All right. So just think about the processes that you can go through in terms of thinking about how can I get this if I get stuck. So if I get stuck here, can I do something like this to kind of get me through the process? All right. Just think of the different processes that you go through. All right. So let's look at number 6. Number 6, we have this for number 6. All right, we have the square root of 14 m to the 5th times the square root of 7 m to the 13th. All right, now the way I would do that is you have variables involved, okay? Now, I would go ahead and deal with the numbers, pull out the numbers first. So rewrite this as the square root of 14 times the square root of m to the 5th times the square root of 7 times the square root of m to the 13th. Okay, and then what I would do next is I would kind of put these on the side of each other just to start thinking about this. I have the square root of 14 times the square root of 7, and then this right here will be the square root of m to the 5th times the square root of m to the 13th. All right, because that's really what's happening. So you have 1, 2, 3, 4. 1, 2, 3, 4. And see this right here? What I would do whenever you have variables, I would go ahead and use the rule. Remember the rule, the product rule for exponents. If you have m to the 5th times m to the 13th, when you multiply like bases, you add exponents. So that's m to the 18th. So this right here becomes the square root of m to the 18th. Okay, that's the way you want to do that. All right. It's always easier. It's always easier to simplify these when you write the radicals as 1 when you have variables. Right here, what I want you to think about, instead of saying 14 times 7, instead of saying 14 times 7, instead of saying 14 times 7 like this and saying, well, that's going to be the square root of, and then you got to figure out, well, what is 14 times 7, right? Well, 14 times 7 is 98. But I want you to think, instead of saying 14 times 7 and write it as square root of 98, then let's think about this 14. See, there's a 7 here. That's a prime number. Is 7 a factor of 14? And the answer is yes. So I can write this right here as the square root of 2 times the square root of 7. That's this right here. And then I have this square root of 7. And so square root of 7 square root of 7 is 7, right? And then we know that the square root of m to the 18th, 18 divided by 2 is m to the 9th. And so what I have then is the square root of 2 times 7 times m to the 9th. Y'all agree? Now I'm going to go ahead and put the square root of 2 in the end. So I'm going to get 7 m to the 9th square root of 2. So that's what I get. Okay? Now remember the thought processes. The thought processes are the important things that go along here. Now remember what some students will also do is this. They'll also do this. They'll just go ahead and just multiply these two as one radical. And there's nothing wrong with that. 14 times 7, they'll use our calculator. 14 times 7 is 98. So you get the square root of 98. M to the 5th times m to the 13th. When you multiply like bases, you add exponents. 5 plus 13 is 18, right? And now you got to figure out, well, what perfect square goes into 98? And that's not a difficult one. So you think of your perfect squares you think of your perfect squares. So for example, 4. All right. So let's see if 98 is divisible by 4. So we say 98 divided by 4, and it's not because I get a decimal. So let's try the next one. Let's try 9. 98 divided by 9, and it's not. So let's try the next one. You just go through these processes. So the next one is 16. So 98 divided by 16. It's not, right? And obviously 25 is not going to work because the last digit is not 5 or 0. So let's go to 36. So 98 divided by 36 gives us that. So that doesn't work, right? So then the next one is 49. So 98 divided by 49 gives us that. And hey, there it is. So now I'm going to write this as the square root of 49 times the square root of 2 times the square root of m to the 18th. And that's what we did in one of the worksheets that you learned previously. And I can simplify this. I can simplify this. And so I get 7 times the square root of 2 times m to the 9th. And it's sometimes you can, there's nothing wrong with leaving the answer like this, but if the m to the 9th looks like it's under the square root, you're not going to get all your points. So make sure you're aware of that. So that's going to, so another way you can write this is you could say, well, that's going to be 7 m to the 9th times the square root of 2. So either one of those is fine. Okay? All right. Number 7. So let's look at number 7. Number 7, let's suppose we had this problem. The square root of 15 times the square root of 27. And I'm making, I know there are no variables here, but I'm bringing this to just remind you about something. So what many students are going to do is they're going to go ahead and multiply these two together. So they're going to say, well, that's going to be the square root of 15 times 27, which gives us 405. But then you got to figure out, all right, is there a perfect square other than 1 that goes into 405? And so you got to determine that. Let's see, 405 divided by, let's try 25. 25, and that gives us 16.2. So it's not 25, right? So let's try 9. 405 divided by 9 gives us 45. All right, so that works. But is 9 the largest? I'm asking you. 9 times 45 is 405. So 9 is a perfect square that goes into 405. But is that the largest? No, because what else besides 1, what other perfect square goes in this 45? And the answer is 9. So 9 times 9 would give us 81. So 81 is actually the largest. But Some of you are not going to think like that. You should, but you're not going to think like that. So if you just say 9, there's nothing wrong with that. You just have to go a little bit further. So let me just remind you. And you saw this in a previous lesson. So some of you are going to say, well, that's going to be 9 times the square root of 9 times the square root of 45, right? And then the square root of 9 is 3. And then you got to think, okay, can I simplify the square root of 45? And I can because 9 will go into 45 evenly. So that becomes the square root of 9, square root of 5. Square root of 9 is 3. So I get 3 times 3, square root of 5. And 3 times 3 is 9. So the answer is 9, square root of 5. Okay? What some of you remember, we did not use the largest perfect square. We now know that the largest perfect square is 81. So this becomes square root of 81. So 405 divided by 81 gives us 5, right? And so that sums 5, and so I get 9 square root of 5. So you see, it's so much easier to always use the largest perfect square. So that way, if you don't use the largest, you have to go through all this process. Now, another way I want you to think about this is what we talked about earlier. So rather than just multiplying these two together, can you think about this strategically? You're dealing with square roots. So this 15 is the prime factors of 15 are 5 times 3, right? And then if you think about 27, you have this will be 9 times 3, correct? So what I want you to think about is this. I can write this as the square root of 5 times the square root of 3, and I can write this as the square root of 9 times the square root of 3. You'll agree? And then I want you to notice the square root of 3 times the square root of 3 right here. That is just 3. So I get the square root of 5 times 3. That's this right here. And then the square root of 9 is also what? 3. So 3 times 3 is 9, and you get 9 square root of 5. All right. So think about all these different ways in which you could get that answer, and that's important that you go through that thinking process. All right. Number 8. Number 8, let's suppose we had the cube root of 11 times the cube root of 7. So as long as the indices are the same, then I can write this product as one radical. So that will be the cube root of 77. And there's nothing you can do there. You can't go any further with it. And the reason is because notice 11 is a prime number, 7 is a prime number, and they're different prime numbers. So there's nothing you can do there, and it's a cube root. Okay, so the only perfect cube that goes into 77 is 1. So you're done with that one. Number 9, let's suppose we had the cube root of 2x to the 7th y times the cube root of 4x cubed y to the 8th. All right. Now, what I would do is there's really no shortcut here other than the noticing that this 4 right here is 2 times 2, and then you would have 3 factors of the cube root of 2. It is so much easier just to write this as one radical and then go from there, and that's what I'm going to do here. So this becomes a cube root of 2 times 4 is 8, and then I have x to the 7th. I want you to think about this. X to the 7th times x to the 3rd is x to the, remember, multiply like bases, you add exponents, so that's 11, right? So, I'm sorry, 10. So that's x to the 10th. And then we have y times y to the 8th is y to the 9th. 1 plus 8 is 9. And then the rest of this is what you've learned previously. So now I'm going to rewrite this as 3 radicals. So I get the cube root of 8 times the cube root of x to the 10th times the cube root of y to the 9th. 8's a perfect cube. That's 2, right? Now think about this. 10 is not divisible by 3, so we got to simplify this further. So what is the largest whole number less than 10 that's divisible by 3? And the answer is 9. So I'm going to rewrite this as the cube root of x to the 9th times the cube root of x. Okay, that is this. This 9 is divisible by 3, so right away we know this is going to be y to the, that's times y to the 3rd. And so now simplifying this further, I get 2 times this is x to the third. This is the cube root of x. I can't simplify that any further because the exponent of 1 is less than 3 times y to the third. And I'm just going to go ahead and rewrite this so that the radical is on the end. So I get 2x to the third, y to the third, times the cube root of x. And so that's the answer. Okay? All right, number 10. Number 10, let's suppose we had, okay, let's see. All right, number 10, let's suppose we had the cube root of y to the 15th times the cube root of 16 y to the 14th. So there's no easy way to do this other than writing this as one radical. All right. Now, actually, you could see 15 is divided by 3, but I wouldn't do that just yet. I would just go ahead and put those two together, and I'll come back and show you what this would be if you dealt with this. But I'm going to write this as 1. That would be the inclination that most students would use anyway. So I'm going to write this as a cube root of 16. We know that y to the 15th times y to the 14th. 15 plus 14 is 29, so it becomes y to the 29th power. Okay, now we can simplify this, so that becomes the cube root of 16 times the cube root of y to the 29th. Okay, the cube root of 16, the 8's a perfect cube that goes into 16, so I can write this as a cube root of 8 times the cube root of 2. 29 is not divisible by 3, but the largest whole number less than 29 that's divisible by 3 is 27, so I can write this as a cube root of y to the 27th times the cube root of y squared. And so now the cube root of 8 is 2 times the cube root of 2. 27 divided by 3 is 9, so that's y to the 9th. And then I cannot simplify this any further because 2 is less than 3. And so therefore I get 2 y to the 9th. All right, now I want you to think about this. I'm going off the side and showing you the cube root of 2 times the cube root of y squared. I can write this as one cube root now because the indices are the same. So that's 2y squared. So it'll be the cube root of 2y squared. So just remember, it's the cube root of 2y squared. Okay, and that will be what you would do there. What I want to do is come back and rewrite this again and just kind of show you what some of you may have done. You just got to be careful. All right, so some of you may have done this. So some of you may have noticed, hey, 15 is divided by 3. So could I just simplify this part right away? Yeah, you could. 15 divided by 3 is 5. So the cube root of y to the 15th is y to the 5th, because y to the 5th times y to the 5th times y to the 5th is y to the 15th. But then you have an issue here, though. So then you got to think about, all right, well, this, I'm going to have to go ahead and write this as a cube root of 16, and then the cube root of y to the 14th, right? Okay? And so then you get this. You get y to the 5th times, and this will be 8 times 2. So it'll be the cube root of 8 times the cube root of 2. And then the largest whole number, less than 14, that's divisible by 3 is 12. So it'll be cube root of y to the 12th times the cube root of y squared. Okay? So it's not much any easier. It's probably easier in terms of thinking processes to go through this. So then you get y to the 5th times the cube root of 8 is 2. I cannot simplify the cube root of 2, so I have to rewrite it. 12 divided by 3 is 4, so the cube root of y to the 12th is y to the 4th. And then I get the cube root of y squared. So then you got to think now, be careful. You see you have that y to the 5th times the y to the 4th? Okay, you got, when you multiply by bases, you add exponents. So y to the 5th times y to the 4th, y to the 5th times y to the 4th is y to the 9th, and that's where we got this. All right, so that's 2 y to the 9th, and then don't forget to put these two as 1, so that'll be the cube root of 2y squared. Okay, so it did not matter which approach you took. You could have simplified this first. All right, okay, number 11. So in number 11, let's suppose we had this for number 11. We had the square root of 2a to the 9th b to the 8th times the square root of 22, a to the 8th, b to the 7th. That's a 7 right here. That's a 7. Okay, now again, I would just go ahead and write this as one radical and then simplify. That's the way I would approach this one. So I would get 2 times 22 is 44, so I get the square root of 44. A to the 9th times a to the 8th. So when you multiply like bases, you add exponents. 9 plus 8 is 17. So I get square root of 44, a to the 17th, and then let's talk about the factors of b. b to the 8th times b to the 7th is b to the 17th, right? I'm sorry. B to the 15th, excuse me, b to the 15th. Okay, so that's what I have. Now let's go ahead and simplify this. So that's become the square root of 44 times the square root of a to the 17th times the square root of b to the 15th. And the perfect square that goes into 44 is 4, so it'll be the square root of 4 times the square root of 11. I can simplify this because 17 is greater than or equal to 2, the index, but 17 is not divisible by 2. So let's think about the largest whole number, less than 17, that's divisible by the index, which is 16. So I get the square root of a to the 16th times the square root of a. For this one, we're going to use b to the 14th. So the square root of b to the 14th times the square root of b. Okay? So then this becomes, let's simplify what we can. I can simplify the square root of 4, that's 2. I cannot simplify the square root of 11. I can simplify the square root of a to the 16th, that's going to be a to the 8th. A to the 8th times a to the 8th is a to the 16th. I cannot simplify the square root of a. I can simplify the square root of b to the 14th. 14 divided by 2 is 7. I cannot simplify the square root of b. So now I'm going to put these factors in front. So that's going to be 2a to the 8th, b to the 7th, and then I'm going to write this product as one square root. So that's going to be the square root of 11, ab. So remember, the square root of 11 times the square root of a times the square root of b is going to be the square root of 11, ab. Okay? All right, and then again, always make sure whenever you have a radical with variables underneath, put that at the end. And so that's the answer. All right, so that's number 11. Number 12, let's suppose number 12, we had 5 times the square root of 18 times 4 square root of 20. All right, now let's think strategically. So what I would probably do there, instead of saying 18 times 20, let's think about 18 and let's think about 20. So I know I can write 18. 18 is even, 20 is even. So I know I can write 18 as 9 times 2, right? So I get 5 times the square root of 9 times the square root of 2. You see that? And then that's a nice one right here. That's 3. And over here, I know I can write this as 4. This 4. And then 20 I can write as 4 square root of 4 times square root of 5. Correct? See what I'm doing? All right. And so then, and then now that's easy to deal with. So that's 5. This right here is times 3. I cannot simplify the square root of 2. This is times 4. This is square root of 4 is 2, so that's times 2, square root of 5. And now you have 5 times 3 times 4 times 2. So 5 times 3 is 15. 15 times this 2 is 30. 30 times 4 is 120. So you get 120. And then the square root of 2 times the square root of 5 is the square root of 10. Okay? Now, I just want to show you the other way. So the other way, what some students are going to do, and that's nothing wrong with that, they're just going to go ahead and multiply these two together. First of all, 5 times 4 is 20, correct? And then you get the square root of, and then just multiply 18 times 20. So 18 times 20 gives us 360. But then you got to think about what perfect square goes into 360. And that's easy to see right away. You see that 36. So that's easy to see. So I get 20 times the square root of 36 times the square root of 10. And then I get 20 times the square root of 36 is 6, square root of 10. And then 20 times 6 is 120, square root of 10. Okay? So it does not matter which approach. It is important, though, that you understand both approaches, because sometimes when doing one, you may get stuck. And so you go back and you try another one. All right, let's do a couple more because we're getting pretty long on this. And I think you should have enough now to get you through this topic. Okay, we're going to do, so this would be 13. Let's do 13. So in 13, let's suppose we had the fourth root of x to the 14th times y to the 12th times z to the ninth times the fourth root of x to the 8th, y to the 16th, z to the 11th. Okay? Now, notice that the coefficients here are 1, so you don't see any other coefficients at all. So the easiest way is to go ahead and write this as one radical. So the indices are the same, so it becomes the fourth root of, okay, x to the 14th times x to the 8th. So 14 plus 8 is, what's that, 22? Okay, 22. So it'll be x to the 22nd power. Y to the 12th times y to the 16th is y to the 28th power. And then z to the ninth times z to the 11th. 9 plus 11 is 20, right? So z to the 20th. And then all you do now is simplify this further. You know you can simplify these because 22 is greater than or equal to 4, 28 is greater than or equal to 4, and 20 is greater than or equal to 4. All right, so you get the fourth root of x to the 22nd times the fourth root of y to the 28th times the fourth root of z, that's a z, to the 20th. All right, now 22 is not divisible by 4, so let's think about the largest whole number less than 22 that's divisible by 4. And so you know that's 20. All right, so I get the fourth root of x to the 20th times the fourth root of x squared, right? Now this right here, 28 is divisible by 4, so the fourth root of y to the 28th is y to the 7th. Same thing here, 20 is divisible by 4, so the fourth root of z to the 20th is z to the 5th. And then simplifying this, 20 divided by 4 is 5, so that becomes x to the 5th. I cannot simplify this, I'm going to rewrite it. The fourth root of x squared times y to the 7th times z to the 5th. And I'll go ahead and putting this in the back at the end, so I get x to the 5th, y to the 7th, z to the 5th, times the fourth root of x squared. And that will be your answer. Okay? And I think actually let's do this one. Let's do one more. 14. We have the square root of 2b cubed times the square root of 14c to the fourth power. So the square root of 2b cubed times the square root of 14c to the fourth. Now again, this one's easy to where just go ahead and multiply them together as one. And so we get 2 times 14 is 28, b cubed, c to the fourth. And then from that point, we do what we did here. So then using the product rule, we're going to rewrite this as the square root of 28 times the square root of b cubed times the square root of c to the fifth. And then for 28, the largest perfect square that goes into 28 is 4. So it becomes the square root of 4, square root of 7. I can simplify this because 3 is greater than or equal to 2. But the largest whole number less than 3 that's divisible by 2 is 2. So I'm going to rewrite this as the square root of b squared times the square root of b. For this one, you're going to use 4. So it'll be the square root of c to the fourth times the square root of c. Now let's go ahead and simplify what we can. So notice that this is this right here is this, and then this is this, right? So I get 2 square root of 7. The square root of b squared is b, square root of b. I can simplify this, that's c squared, and then I cannot simplify that, so I'm going to write as square root of c. I want you to know, see you have square root of 7, square root of b, square root of c. So you have the square root of 7, square root of b, square root of c. I can write this as one square root now, so it'll be the square root of 7bc. And then here you have 2bc squared, so 2bc squared times the square root of 7bc. And there's your answer. Okay, so that is our lesson on multiplying radical expressions.